Today we have two new speakers visiting us. So Christine Burkesh from the University of Minnesota. She'll be running the second mini course in the afternoon today. And Elena Guardo from University of Catania. She's going to be teaching the first mini course with Adam Van Tuyl, who was our first speaker for today, and he's from McMaster University. So maybe just skip. And Elena's an organizer, yes. Thank you very much. So maybe just welcome our speakers. Okay.
So I hope everybody had a good weekend, and welcome to the second week of the school. This week we're going to kind of push forward the how far we get in commutative algebra. We were learning a lot of background last week, and this week we'll try to take you to the edge of what's current. Today's my talk isn't that current. I'm going to talk to you about Hilbert functions of points in Pn. And as a reference about Hilbert functions, I know Fred talked to you about this. A good reference for the stuff I'm going to talk about is Bruns and Herzog's book, chapter 4. And I'm going to really be focusing on kind of one result of Jeremita, Marosha, and Roberts from 1983. Now, there's this saying that a result is classical if it was proved before it was proved before you were born. So for many of you, I wish I was classical for me, but it's not classical for me. But I'll prove this result or give you the statement of what a Hilbert functions of points in Pn is. Okay. So I'm going to start off with just kind of quickly running through what do we mean by a point in Pn. Claudia mentioned a little bit about this last week. And so I'm going to try to bring in, where possible, things that you saw last week. Okay. So what is a point in Pn? So just to make life easier for ourselves through this talk, I'm going to let just K be the complex numbers, and R is always going to be my polynomial ring in n+1 variables, right? And Claudia introduced to us what Pn is, right? Pn is the set of all n+1 tuples minus the origin with an equivalence relation, okay? So this here is an equivalence relation. And how does this equivalence relation work? Well, we say the pair A0, A1, or the n+1 tuple is equivalent to the tuple B0 up to Bn if and only if there exists some, I guess it has to be non-zero element in my field K, such that the first tuple is a scalar multiple of the second tuple, right? So B0 up to Bn is equal to lambda of A0 up to lambda An, okay? So this is an equivalence relation, right? And so you have equivalence classes. And so a point is just one of these equivalence classes, okay? So we A0 and then colon A1 colon up to An denotes the equivalence class of a particular point, right? Or A0 or n+1 tuple. And this is what we would call a point in Pn, okay? So this is a point in Pn. Okay? And so the point of the lectures, what I'm doing and what Elena will be doing later in the week, is we want to study collections of these guys. Okay, so our object of study is we're going to look at finite sets of points, P1 up to Ps, inside of projective space. Okay, and Elena is going to show you a little bit more fancy thing where she'll look at points in multi-projective spaces. Okay, so that's what we want to do. Okay, and you may think, well, why? Okay, so what is some motivation of why you would want to do this? Well, in some ways, the first reason you might want to be interested is they're kind of like the simplest geometric object you can study. Right, so simplest geometric object. Okay, well, okay, that's one reason. Another reason is sometimes that you may be studying sort of more complicated geometric things, and you can kind of cut it with a hyperplane or hypersurface, and you can get a collection of points. And somehow those points will tell you something about your original variety. Okay, so I'll just say, this is very vague, but arises in, say, hyperplane sections. So let's say, for example, you have like some sort of curve, and this is sitting inside a projective 3 space, and somebody comes along and like chops it with a plane, right? So let's see how good my drawing skills are today. So you can see like this curve going in and out of the plane, and I have like, it hits the plane in 3 points, and somehow information about those points tells you about something that you started with. Okay, so the points in the hyperplane, or the plane or the line, depending upon where you're working, tell you about original variety. Okay, and I know some of you were here 2 weeks ago when we had the applications program, and in a couple of the lectures we even saw points showing up, in particular in the coding theory lecture, and also there was the lecture on splines. You can go back and watch these online. You know, at some point people reduce the particular problem to understanding properties of points in projective space. Okay, so this is part of the reason you want to study it. Okay, and the thing that I'm going to focus on is one aspect is the Hilbert function of these particular points. Okay, now any questions about that, about why you would want to do that? No? Okay. Okay, so let's talk about the thing. We're all in commutative algebra here, right? This is a lot of geometry, and everybody got a little scared. So let's put the geometry away and like bring back in the algebra, right? So talk about the ideal points in projective space. Okay, so what can we say about that? Okay, so Fred mentioned this and Claudia mentioned this, is about things being homogeneous, right? We have to talk about homogeneous polynomials. So I know you guys all had a very good time on the weekend, so you probably forgot everything. So let me remind you, all right? So an polynomial in R is homogeneous if all its terms have the same degree. Okay, so I always like to give 1 or 2 examples of these, right? So let's say 3x0 cubed plus 2x0 x1 squared plus, say, 2025 x2 cubed. Okay, so this guy is homogeneous. Right, and let's make something that's not homogeneous, right? And the address of fields, what is it? 22, or 222 something college, right? So x cubed plus 2025 x1 to the 17, right? So this is not homogeneous. Okay, so we have a homogeneous thing and not homogeneous things. Okay, and the definition the ideal of a point is it's going to be all the set of homogeneous polynomials such that when you plug the point in, you get 0. So ideal of a point P inside a projective space. This, here I'll write it like this. This is the ideal generated by all the elements F, such that F is a polynomial, of course. F is homogeneous. And f of p equals 0. So when you plug in your point, you get 0. Okay. So just, I'm not sure how much algebraic geometry some of you have done before. So let me just kind of step back and explain, why do you care about this homogeneous condition, okay, when you're working with points in projective space? Okay. So note, we need f homogeneous to make sure the definition, or to make sure that fp equals 0 is well defined. Right. And so what do I mean by that? Well, a point, right? A point is not just one object. A point is a set, right? A point is an equivalence class. So what does it mean for a polynomial to vanish at a set, right? It makes sense to talk about what it means for a polynomial to vanish at a tuple, right? But what this is really saying is, not only do you want to vanish at the representative of the set, but you want it to vanish at every element inside of that set, okay? And that's why we need the homogeneous part to make sure that it vanishes at everything on that set. Okay, so sometimes it's a little easier to see how this works in an example. Let's say I take the point 1, 2, 3. So there's my projective point. And here is my polynomial, x0, x1, x2. And it is 6x0 squared minus 2x0, x2 minus 3x0, x1 plus x1, x2. Okay, so this is a homogeneous element. Hopefully everybody's convinced it could be a homogeneous element. And when I plug in 1, 2, 3, I get 6 times 1 squared minus 2 times 1 times 3 minus 3 times 1 minus 2 plus 2 times 3, and it's 0. Okay, but this is only one representative of this particular equivalence class, so we want to make sure it works for everything. So we can remember everything that is in the same equivalence class is just a scalar multiple. So let's just put any scalar multiple inside of our function, and let's see that it vanishes, right? And you can check for this guy. You get 6 lambda times 1 squared minus 2 times lambda times 1 lambda times 3 minus 3 lambda 1 lambda times 2, and then I have minus lambda 2 times lambda 3, right? And the homogeneous part, and I think Fred referred to this, is like part of the homogeneous definition is you can pull out, you know, the scalar multiple, right? So they all have a lambda squared. So you're getting lambda squared times 0. Okay, so you get 0. Did I forget? Oh, it's a plus. Yeah, a plus. There's a plus over there. Okay. So then when you do the board, you can't see the rest of the board. Okay, too close. Okay, so this makes sense. Okay, it makes sense. And so what we have is that our f here is in the ideal of this particular point right here. And this is one of the homework questions, okay, is that if your point, if you take just a general point like this, and let's say that the first guy is not 0. I'm doing a special case here. Let's just assume that the first one is not 0. Then the ideal, if I call this P, the ideal of this point, make sure I get this right, A1 x0 minus A0 x1, A2 times x0 minus A0 x2, all the way up to A n x0 minus A0 xn. Okay, you can actually write down explicitly what the set of generators are. Okay, I'm doing a special case, and then your homework is also to convince yourself what happens if the first coordinate is 0. How do you solve the problem? Okay, and part of the question that I gave in the homework is actually prove that this is a Grosvenor basis as well. Okay, so you can use some of the stuff you learned from Fred's lecture. Okay, any questions about that? Okay. Okay, I want to dump a lot of terminology on you for a second. Okay. Some of these Sarah told you last week, but let me just review them again. So we say that an element in a quotient ring, right? So this is, I'm writing L bar for the coset representative of L is a non-zero divisor. Oh, I wanted to use J. Is a non-zero divisor if Well, there's many different ways of writing this, but I'm going to write it as whenever L times F is in the ideal J, then F is inside of J. That's one way of writing a non-zero divisor. We have L1 bar, L2 bar, up to Ln bar inside of Rj is a regular sequence if Li bar inside of the ring R mod and J, L1 up to Li minus 1 is a non-zero divisor. So L1 is a non-zero divisor on the first ring. Then we throw L1 into the ideal J. L2 is a non-zero divisor on the new ring, and so on. Okay, so that is a regular sequence. I think Sarah mentioned that one. One term I don't think Sarah mentioned is the idea of a complete intersection. So we say that L1 up to, or the ideal J is a complete intersection if J is generated by L1 through LS, and L1 bar up to LS bar is a regular sequence on R mod out by the ideal 0. Okay, so it's just saying L1 is a regular non-zero divisor on, yeah. L bar. Oh, where am I looking? Recall, where am I looking? All right, too many people at once, Stephen. Oh yeah, there. There we go. Everybody happy? Okay. Okay, so we have a complete intersection, and then the depth of R mod J is equal to the length of the longest regular sequence, and then the dimension, Fred mentioned this the other day, is the length of the longest chain of prime ideals. Okay, so equals to the length of the longest chain of prime ideals. Okay, so we didn't really talk about prime ideals so much, or chains of prime ideals in any of the courses, but as Fred mentioned, it's kind of a measure of the size of the ring. Okay, now the reason I'm doing all this is because I'm trying to talk to you about the ideal points of Pn, and there's lots of nice properties about the ideal points in Pn. Okay, any questions about that? The way that I've defined, in general, we don't need any of this to be homogeneous. Okay. Yeah, I mean, I'm just putting the general definitions up here. I mean, we're going to be moving everything into the homogeneous case, right? The last one has to be, you know, I never work in the non-homogeneous case, right? So I don't actually, that wouldn't happen because you wouldn't get one in the ideal. Yeah.
Regular element to non-unit non-zero divisor.
Yeah.
That does it for you.
Right. I don't know if you heard what Tricia said. You could define a non-unit, a regular element. Yeah. In the land where I work, it never comes up. So. Okay, so what did I want to say about all of these things? Okay, so you have the following facts, and I actually put them down as homework problems for you, is that this ideal here, one of the nice properties is that it's a prime ideal. So this ideal is a prime ideal. It's a nice property to have, but actually it has even a nicer property that it's a complete intersection. So IT is a complete intersection. Right, so I've given you the generators in the special case over there. So now you just have to verify that that gives you the regular sequence that you're looking for. And the other property that I wanted to point out is that the dimension of this ring is equal to 1, which is the same thing as the depth of this ring. And as Sarah mentioned last time, dimension, when dimension and depth are the same, that means that you have a Cohen-Macaulay ring, right? So this, if you know what that means, it means that our IP is Cohen-Macaulay. We're not going to make a big deal about it in today's lecture, but I just wanted to point that out. Okay, so an ideal of point has some pretty nice properties. It's a prime ideal, it's a complete intersection, and you also get some, it's a way of building Cohen-Macaulay rings. And so I erased it, right? But I'm interested in collections of points, right? So we want the ideal of points. So given a set of points, P1 through PS inside of Pn, the ideal of X is the ideal that you get by intersecting each of these homogeneous ideals. So you take the ideal of each point and then you intersect them in here, right? And so just as a remark, it should be clear that f is inside of Ix if and only if f pi equals 0. Right? So it's the collection of all homogeneous polynomials that vanish at every point inside of your set. Okay. And one lemma here that I'm going to put, I won't give you the proof, but you can find my lecture notes. They're handwritten, but I included a proof in the lecture notes, so you can see it later, is that we know that the depth is 1, but we can say a little bit more about so the depth is 1 means that I can find a regular sequence of length 1, but we can say a little bit more about that regular element. Okay, and it's a useful fact to have. So let X be a collection of points, P1 through PS, inside of Pn. Then there exists an element, homogeneous element L of degree 1, such that the class of L is a non-zero divisor on R mod R. Okay? So it's a pretty handy little lemma to have. Okay. And so we're still saying some properties about the ideal of points. So we know some properties about what a point is, right? The ideal of a point is complete intersection and prime. But what about this guy, which is the one that we're interested in? Well, we have the following facts. Okay. The ideal is radical. So when you take the radical of the ideal, okay, you get the ideal itself back. And what else do you have? You have that the dimension of this ring is equal to the depth of this ring, and it equals 1. Okay. One of the homework assignments that I gave you is to prove that this ideal, the ideal of a set of points, is prime if and only if it's a single point. Okay. But there are examples of points that are complete intersections that are not single points. Okay, so there are some differences, and those are all part of the homework assignment. Okay, so these are some basic properties, and kind of the reason I wanted to do this is just to add another remark, is that in some ways, ideal of points have many similar properties to square-free monomial ideals. Okay, so let me make this precise here. So Ix has properties similar to square-free monomial ideals. Okay, ideals. Right, and which properties is it similar? So in particular, Ix is the intersection of prime ideals, all of which are complete intersections. When you take the primary decomposition of this ideal, it breaking down into, well, obviously it breaks down to prime ideals, but also each of the prime ideal is itself a complete intersection. I thought Sarah was going to talk about primary decomposition when I wrote my lecture. She didn't, but this is exactly the same sort of property that a square-free monomial ideal has. When you take a square-free monomial ideal and look at its primary decomposition, you get each of the primes, you get a bunch of prime ideals, and each of those prime ideals are complete intersections. Okay, it's a little bit more general in the monomial case because here all your associated primes have the same height. Okay, but they have sometimes things that you can do with square-free monomial ideals you can do over for ideals of points as well. Okay, so that's another reason why they're kind of interesting. Okay. Any questions about that? No? Okay. Okay, so let's talk a little bit about Hilbert functions and Macaulay's theorem. Okay, so it was really great. Fred did a lot of the groundwork for me. So hopefully everybody, you know, while you're on your trip to Niagara Falls, you were like reviewing your lectures on Hilbert functions, right? So what we're going to do is we're going to fix a positive integer, fix d, and we let r sub d be all the elements in my ring such that f is homogeneous of degree d, right? So we have the collection of all homogeneous polynomials of degree d, and if I is homogeneous, then I sub d is what you get by taking your ideal and intersecting it with this space right here. Okay, so it's the collection of all homogeneous things of degree d inside of your ideal. So here's the following fact, and I left it for you as a homework, and you should do this at least once, right? Is that R sub d is a K vector space, right? You should go back to your linear algebra and actually check that this is a K vector space. And more importantly, that ID is a subspace of RD. Okay, so these guys are actually vector spaces, right? K vector spaces. And you actually have to cheat a little. I want to point out you have to kind of cheat to make this work, okay? Because, and this is something my students always forget when I teach linear algebra, is a vector space always needs 0, right? And so we have to make one little cheat here to make this work, is we assume that 0 has every degree, okay? So to make this work, need to assume that 0 is in RD or all D, right? So the degree of 0 is everything, right? You can have in order to make it work, okay? Just so that you can check all the definitions, okay? Okay, great. We love vector spaces, or I love vector spaces, okay? They're a lot easier to think about. And, you know, once you learned about a vector space, the next thing you want to know is about the size of your vector space. And that's where you learn about bases and, you know, dimensions, okay? And the Hilbert function is really just a way of kind of recording a whole bunch of these dimensions, okay? So let me write this. Okay. So we're going to get to that in a second. So these are all vector spaces, and we want dimensions. And so let's start with this guy. This is a K vector space, and Fred already told you the dimension. So this is your challenge. Do you remember? No, but Fred used a different notation. He used a different polynomial ring, so it's a little trickier. But the dimension of this vector space for each d, anybody remember what it is? Yeah, m plus d, choose d. Okay, so one thing you should come away from these 2 weeks is knowing this formula. Okay, and Fred mentioned that it's related to the bars and stars argument. So let me give you actually that connection here. Right, so why is this, right? Well, a basis for RD is all monomials of degree d in your n+1 variables, right? So what we need to know is we need to know the number of things in this set. We need to count all these monomials where d0 up to dn is equal to d, and we have to have that each of these exponents are 0 or bigger. Okay. Now, if any of you have taken a combinatorics class, right? Or well, let me back up. So really, it's not the monomials that's important. It's the number of integer solutions to this guy, right? So this is equal to the number of integer solution to z0 up to zn equals d, with zi greater than equal to 0. Right? I said z properly, everybody? Okay. Okay. And so this is equal to the number of ways to place n bars and d stars, okay, in n plus d spots. Okay, but what does this mean? Okay, this is a little vague here. So it's actually easier just to do a quick example. Right? So let's say that I'm looking at, I'm going to look at the polynomial ring in 3 variables, x0, x1, x2, and I want to look at d equals 5. Okay. So what does a monomial look like of degree 5 in this ring? Well, I can give you 2 examples. I could have x0 squared, x1 squared, x2, and here's another one, x0 cubed, x2 squared. Okay. So this is giving you an integer solution to this equation, right? I can think of this as telling me 2 plus 2 plus 1 is 5. This monomial here is telling me 3 plus 0 plus 2 is 5. Okay, right? I'll give you those 2 solutions there. Okay, but now what's important here is kind of where the plus signs are and how many and what the value is in each particular entry, right? So I can have 2 stars, and then I have a divide, and then I have 2 stars, and then a divider, and then I have my 3rd star, right? So 2 stars, 2 stars, 1 star gives me this equation, which gives me this monomial. This guy over here would be 3 stars, then a divider, then I have no stars, so I have another divider, and then I have 2 stars, okay? So what you're doing is you're taking 7, you have 7 spots, right? 1, 2, 3, 4, 5, 6, 7 spots. So 5 plus 2 spots. And what you're doing is the dividers correspond to the plus signs, right? So this equation here has, you have n plus 1 values, but you have n dividers, right? So we have 2 dividers and 5 stars, right? So that gives me 5 plus 2. Oh, sorry, you probably can't see that at the back. 5 plus 2, choose 5, right? Which gives me 21. There are 21 different ways of doing that. Okay, so if you haven't seen this before, right, it's a nice little exercise about how you compute all the monomials of a particular degree. Questions about that? Can you guys all read it at the back? So when I'm teaching, I always feel like I need a joke or something while I'm rubbing out the board. So I thought of one, or I found one. Okay. So while I'm rubbing out the board, I'll tell it to you. Okay. So why can teenagers only count using odd numbers? Because they just can't even. It's called what?
Cows and fences.
Oh, cows and fences. Okay. You didn't like my joke. You wanted to go back to this. Yeah. No, actually, that's a good idea. I'm going to use that next time I teach combinatorics. Okay. Okay. So we've gone a long way, right? The title was Hilbert functions, and here we are. We haven't even seen a Hilbert function yet. Well, we have. Fred did it before, right? So let R inside of R, I inside of R be a homogeneous ideal. Okay. The Hilbert function of R mod I is the function H R sub R mod I going from n to n, and it's defined by taking an integer. I use D. Taking D and mapping it to the dimension of the d-graded piece of the ring minus the dimension of the ideal in the d-graded piece. Okay. Okay. Because it's a subspace, you know, this number is going to be positive. Okay. Fred defined it in terms of the quotient, but this is the exact same definition. Okay. And depending upon where you look, right? So the convention sometimes to write your Hilbert function is like R0, R1, or not R, H0, H1, H2. So you write it as a list of numbers or a sequence of numbers, or you might see it sometimes written like this, okay, as your sequences like this, okay? It's important to note n includes 0, okay? So you start your counting at 0. 0, your ideal is usually empty in that case, and this guy is 1. Okay, it's dimension of the ring. Make sense? Okay. Okay, so this function is great, right? And it's almost something you can explain to your linear algebra students if they ever internalize the definition of dimension. But we're interested in something more interesting, right? And something Fred didn't talk about is like, you have a list of numbers, right? How do you check if it's the Hilbert function of something, right? So, okay, these things exist, but what numbers can you get, you know, thrown out of this function? And that's what I want to talk about. Okay, and that's going to correspond to Macaulay's theorem, which somewhere I wrote that down. Oh yeah, Macaulay's theorem. Okay, so we're going to define, and then this is the first time you've seen it, probably the weirdest function you've ever seen. Okay, so we're going to talk about the ith binomial expansion of an integer a. Okay, so given integers a and I, a can be written, I guess this is really a definition and lemma, because you have to say it can be written uniquely, because you have to prove that it can be done uniquely. It can be written uniquely as a is equal to mi choose I plus mi minus 1 choose I minus 1 up to mj choose j, with kind of the numerators of these binomial coefficients are strictly decreasing until you get to mj, which is greater than or equal to 1. Okay, so given any two numbers, you can write it as a sum of binomial coefficients, and you can do it uniquely. The one piece of information you need at the beginning is the I. Where do you start your first binomial coefficient? Okay, and what we're going to do is we're defining a function. We define a function, and I'm going to write it as upper I going from n to n. Okay, so upper I n. And the way this function works is I take my func a, I write it in terms of the ith binomial coefficient. and I'm going to send it to A upper I. And A upper I, what it does is it adds 1 to both the top and the bottom of your binomial coefficient. You get mi plus 1, I choose plus 1, plus mi minus 1 plus 1, choose I, all the way down to mj plus 1, j plus 1. Okay, so it's kind of an interesting function because the very first thing that you do is you actually have to first translate your number into the proper way of writing the number, and then you can stick it into your function. Okay, and then you would collapse it all back to give yourself an integer. Yeah.
Sorry, I may have missed this, but are the mi all the way down to the mj?
Yeah.
Is the switch from?
Yeah. Sorry. That should be not strictly, and then this could be greater than or equal to, well, I guess it's j, I guess, because it can't go any less than j. Okay, so the last one can be equal to the j there. Okay, okay, this is a little easier to see with an example. Okay. So if I take A is 17 and I is equal to 3, and I want to compute A upper 3, I guess 17 upper 3, what is that? Okay, so you take 17, you take your 17, and you want to write it as a binomial, a sum of binomial coefficient, where the first binomial coefficient has a 3 at the bottom. And the way you do this is you pick the largest number you can without going over 17. Okay, so 5 choose 3 is 10, right? But 6 choose 3, 6 choose 3 is can't do it, 20, right? So I can't use a 6. I have to use a 5, and then okay, so I've used up 10 here. So now I look at 7. Okay, I have to write the 7 in terms of a binomial coefficient with 2 at the bottom. The biggest I can do is 4, and then I'm still short 1, so it's 1. Okay, because this is 10 plus 6 plus 1. Okay, make sense about the algorithm? I know it's a bit fast. And then 17 upper 3 is you take those exact same numbers, but then you just say, oh, okay, I'm going to make it 6 choose 4 plus 5 choose 3 plus 2 choose 2, and that gives me 15 plus 10 plus 1, which is 26. Okay, if you've never seen this before, it looks like a crazy function, right? So somehow you take a number, you break it up in a certain way, and then you get a new number popping out. Okay, everybody okay with me on that though? Okay. I'm out of jokes, sorry. Okay, so what do we do with this? Well, we need one more definition. A sequence of non-negative integers. And I'll write it like this: Ci, I going from 0 to infinity, is an O sequence if the first term in the sequence is 1 and Ci plus 1 is less than or equal to Ci upper I for all I greater than or equal to 1. Okay, so the growth as you go down the sequence is kind of dictated by the previous entry. So you're wondering, okay, what happens at the value Ci plus 1? I need to go look at what the previous number is, do all of that, fancy stuff down there. I'll get a number, and that number in the next in the sequence can't be bigger than that. Okay. And here comes the big payoff. So this is Macaulay's theorem, and this is the 20s, but the 1920s, I don't know, remember. So hopefully it's classical to everybody in the room, right? Is that this sequence is the Hilbert function of a ring of the form k x0 up to xn mod I, with I homogeneous if and only if this sequence is an O sequence. If you take anything away, oh, sorry, if you take anything away from this lecture, it should be this guy. I know I haven't got to the theorem about points, but in some ways this is an important result. And if you go on to commutative algebra, you really want to know this result. It's telling you what sequences can be the Hilbert function of a set of points, or not points, just any quotient ring. Okay, and you can actually, it's constructive. If somebody hands you this guy, you can actually build a ring and an ideal with that Hilbert function. Okay, any questions about that? Right, so let me just show you the power of this. So example, somebody on the street in Toronto or maybe in Niagara Falls, right, came up to you and said, hey, here's 1, 4, 10, 17, 27, H5, H6, right? Here's a sequence of numbers, and you can say, hey, this is not the Hilbert function of anything, okay? Is not the Hilbert function of any quotient of k x n, since, and this is important, one as I'm going to point out here, it's always important to remember your counting starts at 0. So 0, 1, 2, 3, 4, right? Since H3 is 17, so H3 upper 3 is 26. That's what we computed on the board. But H4, which is the fourth term, is 27, is not less than or equal to H3 upper 3. Okay? So this can't be the Hilbert function of anything. Okay, so it looks like I'm nearing the end of my time, and I haven't even got to the Hilbert function to point, but that's okay. I can do it. Yeah. Oh, no, I won't. No, it doesn't have to be increasing. There's all sorts of weird questions that you can ask. Is can you have Hilbert functions that go up and down, right? And there are. You have to really work at them. But there are cases where you can make the Hilbert function go up and down as much as you want. Okay. Okay. So the last part here, pass 4, is the Hilbert function of point in Pn. Okay, so we know what all the Hilbert functions are, okay? So the next natural question is you look at your special class of ideals and you want to be able to say, okay, if you're in this family of ideals, I can tell you what the possible Hilbert functions are, okay? And to answer this question, okay, this is what Jeremy, Maroche, and Roberts did, is they actually, for a set of points, an ideal of a set of points, they could actually explicitly describe what all the Hilbert functions are. So we need one more definition. The definition. So given, say, a Hilbert a sequence, you're given a sequence of numbers, the first difference function, function is delta h, and it's the new sequence where you get hi minus hi minus 1, or I going from greater than 0 with h minus 1 is equal to 0. Okay, so as an example, we have, let's say we had h is equal to 1, 4, 10, 19, 30, 40, and 50, and then it keeps increasing by 10. So this is a valid Hilbert function. The first difference function is 1, 3, 6, 9, 11, 10, 10, 10, and so on. Okay, so I'm just taking the first difference. 1 minus 0, 4 minus 1, 10 minus 4, and so on. And here is the punchline. Garamita, Narosha, Roberts in 1983. Okay, so this guy is a Hilbert function of a set of points in Pn if and only if 3 conditions hold. Okay, and those 3 conditions are that the first value is n plus 1, or I guess it has to be less than or equal to n plus 1. The second one is delta H is an O sequence itself. And the third one is that HI is equal to S for all I sufficiently R with S. Okay. Hilbert function, did I have to put? Oh, S point. Hilbert function of a set of S points in Pn if and only if these 3 conditions. Okay. So this, it doesn't seem like a lot. So you're given a Hilbert function, or you're given a sequence, and you want to check if it's a Hilbert function with a set of points. In Pn, the first value has to be less than or equal to n plus 1. That forces you into n. The condition that it stabilizes at S comes from the set that you have S points. And then this fact here, right, when you have the first difference function, the new function you may get may not be an O sequence, but that's the property you get from this property here comes from the fact that you're moving to an Artinian ring, and this is the Hilbert function of some Artinian ring. So that's why you get this guy right there. Okay, the tough part is proving the reverse. One direction is easy. Okay, so I'll have to stop there because Sergio's grabbing the mic. Okay. All right.